So hello and very welcome back to our channel again. And as you can recall from our previous two modules, we are exploring the power of KiCad in electronic design as KiCad, schematic drawing and the PCB drawing software, which allows us to design a real world electronic hardware circuits. And it's a free software, it's an open source. So this into that discussion, this is our third module in continuation with that. And as you can see that we have this schematic ready on our screen, which is an inverting amplifier where we are applying input to the negative pin of the op-amp and positive pin is grounded. There is a negative feedback from output back to the negative pin of the input through this resistor. So it's like voltage amplifier that we are using, and there is this gain provided by a ratio of R1 over R2, which is set to be 10. Obviously, we need a DC power supply, so we are using dual power supply V1 to be 15 volt and V5 to be 15 volt. But since the positive pin of this DC power supply is connected to the source potential, that is ground, which is 0, this will be a minus 15 volts to the negative pin here to the power supply, and to the positive pin we have got this 15 volt here. With that, we have the voltage source, which can be at a time a DC voltage source or an AC voltage source or and time varying voltage source with the specified amplitude peak value of an amplitude and frequency. So there are variety of analysis we have performed in our previous module. In our previous model we have also covered about how to design, how to pick up these components and the devices from the library right here, and how to make the connections amongst them. And also we provided information about how to pick up these voltage sources and how to make those interconnections. Also, we explained few critical points about what is the importance of underscore flag, and so much information we have given. But today's module, so if you are new to this module, we encourage you to refer back to those previous two models on which talks about KiCad and ngSpice, the SPICE model. And because this is the model that we are using is from the manufacturer. Okay, if I double click here, like I showed in the previous section. So here you can see that there is a wealth of information that has come here. And after clicking simulation model, here I have explained in the previous model how I use this integrated circuit OPA 1641 and how I use this model, how I call this model file into this simulation model editor. And all the circuit performance simulations will be based on the performance of that IC. So we are using not a generic model, rather we are using a SPICE model from the industry, that is a manufacturer. Now, in our previous model, we've carried out few analysis, and now I will show you how to do more analysis and how to understand a comprehensive performance of this inverting amplifier using OPA 1641. So let us continue that. So what I'm going to do, I will click this simulator here. Oh, so here you can see I have already performed this analysis right over here, which is showing me the fast Fourier transform of the signal. So how to understand that performance? So for example, there is a signal exactly at, let me show you the peak here, is exactly at 5 kilohertz, just about 5 kilohertz. And where is that coming from? So that 5 kilohertz, let me show you here in the schematic right over here, because I have set the frequency to be 5 kilohertz here. Okay, this is my frequency of 5 kilohertz. If I change it, then the FFT will change. But how did I obtain that FFT? That is the next question. So let me right click here. Let me click the fit on screen. So what I did is I clicked the new analysis tab. which opened me this simulation tab where analysis types are there. So amongst these variety of analysis, I have to choose which analysis I need to perform. So in our previous module, we have successfully carried out DC sweep analysis. We have successfully carried out AC small signal analysis, where we obtained the Bode plot and understood what is the gain and magnitude behavior with respect to frequency of this circuit. And we also performed a transient analysis. Okay, so these three analyses we are done. DC operating point is also there. If you wish to perform that, you can do that, but it is just is going to give you the voltages and the currents at the bias points of the circuit. Then comes the pole zero analysis. There comes the noise analysis. There is an S parameter analysis. For example, if you are designing the RF circuits, you need to you might be in a need to do this and perform this analysis. And then FFT. So we are going to see what kind of analysis we can do right here. So first, let me show you uh, the noise analysis. Okay, that's the noise analysis is the first one. And here I would click over the measured node. Now, which is the measured node? All these nodes are coming here based on what I have mentioned in the schematic. So let me show you the schematic first. Basically, there is a noise in the circuit. So noise is coming from the real parts of these schematic, and what those real parts are. There are resistors, they will produce the noise. There is an operational amplifier IC itself, that is OPA1641. It has its noise performance. Then there are DC power supplies. They are going to contribute their noise, and based on that, you might be want to notice that I haven't connected the filtering capacitors to with the power supply. So when you design the PCB, when you design the schematic, it is often the practice that you apply a supply decoupling capacitors, usually 1 microfarad. From these nodes with respect to the source potential ground. Okay, so to reduce the noise. Okay, and then there are many components that will contribute the overall noise of the circuit, which we can measure at the output. That is called as output noise of the circuit. And then there is the spectral density of that noise with respect to frequency. Okay, and we have to provide the reference node, whether you are measuring the noise at this point with respect to ground or with respect to input or any other potential in the circuit. That's the point. So we'll come back here, and here I want to say that I'm measuring the noise and the output. The reference node is optional. It is default to be at the ground, and you want to specify what is your noise source. So for example, V5 and V1 are my supply voltages. That is the positive and negative supply to the op amp, and V4 is the input signal source. Okay, so we have to specify which one of it is your noise source. So reference node has to be is specified there. What about I specified input as a reference node, and we'll see what the results are now. Okay, so the results are coming there, and it is the one. It is the one. So reference node is input now. And so you can choose the reference node to be input or to be ground. Okay, so this is how it will go like that. So that is about your noise simulations. And I have already told you that, look, reference node, if you don't specify, it is default ground. And then with all these options available, you can actually choose. If we take like VO as a reference node, and we'll see like what is the case, and then we'll run the simulation. Then we'll see there are no results actually. So obviously the correct pattern of this is VO and then V4. Leave it optional, leave it blank, or specify the in. Okay, and then only you will get the results. And that's how we are measuring the results. Now it will plot. It will plot the output results. Still running, and that's it. So these are your noise simulations. Now, next analysis. Go here, click here. I'm clicking here. Now we have successfully performed the noise analysis. What about the FFT? Go to simulation, new simulation tab, select the transient analysis first. To run the FFT, you need to perform the transient analysis first. So let's say time step is 1 milli, final time is 10 milli, initial time, I leave it optional, maximum time step, leave it optional, leave it blank, okay. And once that is done, let me see if I can plot it. Oh, I need to hit the run button. So I will get the input signal waveform. You see now, input signal waveform is there. So if I like show you some part of it, so that's my beautiful input signal. But these I want even finer data points. So I will edit it, and I will, instead of 1 milli, I would say go for 1 micro. So finer steps, very fine. So it will have a smooth output, input output waveforms. So this is how I do it. So now have a look here. The signal is so clean. Now I will click the VO, and that's the performance of inverting amplifier of using op-amp. Once that is done, what I'll do is I will say edit simulation, not the edit simulation. I will say new simulation tab. Remember, FFT can be performed after performing the time domain analysis. So I will go for FFT. After FFT, I want to have the output signal spectrum and even the input signal spectrum, fast Fourier transform of these two, input and output. So I will say, okay. Now it is doing that simulation. Now there is like FFT has been done. Some information about how the FFT was obtained is given right here. So now you can see you have plotted after clicking the output FFT. And here is the like intensity in dB. So it is close to 0 dB. That's your y-axis. And then you have like input spectrum. So that's your input and output. So both are, and the frequency is about 5 kilohertz, which is what we expect. So that's how you go for FFT. Okay, let me just click file and export current plot as PNG. So, or you can have it as a CSV also. In the download, I will say like, give it a name, one, and then I will say save it. You want to ask me replace? Yes, replace. Okay. So I have saved that file with this analysis. So we have successfully also performed the FFT of the circuit, right? We have done noise analysis, we have done FFT, and to obtain FFT, we have to first do time domain analysis. Then I will click, let's say, edit simulation tab, and we'll see there are some other things I can do. There are no signals to be to be available to have a FFT, because VCC and VE are the DC signals. Okay, so we'll remove that now. Okay, so finally, I will show you how to perform an operating point analysis for the circuit. As I said, the operating point analysis will enable us to find out and understand all the voltages and the currents of this circuit based on how we have biased this circuit. As I said, you have plus minus 15 volts to be applied to the positive and the negative power pins of the op-amp respectively. You have the input voltage source at the input of this operational amplifier, and then you are recording an output. So all the currents through resistors, voltage across the resistors, voltage at the output, voltage at the input, currents at the input pins, and the current available to be delivered to the load from the output pin will be available through the operating point analysis. Also, you will also see how much the total current this circuit is drawing from the power supply voltage supplies there. And based on that, current multiplied by the voltage will give you the power consumption. So let us do that. So I will click here, the simulator. It has opened the Spice simulator. Then I will click the new analysis tab. And for it takes a while, just a second to open the simulation tab. Analysis type is OP, that is DC operating point. So I click here. Once I click here, I see the console window is ready, and I will now click run simulation button. And the simulation has started and it ended quite very soon. So here you see that some information about the Spice simulator. Here are our results for the DC operating point analysis. So what you see here, I under in parenthesis, there is a name of the voltage sources, and it says that the current offered by these voltage sources. So V5 is offering minus 1.8 milliamps, V1 is offering minus 1.801 milliamps. So these are our plus minus 15 volts respectively, the voltage supplies. The current drawn from the input signal source, which we applied to the negative pin of the op-amp, offering the current about 1 micron, close to 1 micron. Current through the resistor is close to 1 microamp. And then there is this some other information. These are currents, all these are the currents being drawn by the components inside the sub-circuit. And remember, our sub-circuit is the OPA 1641. So there are all internal components of inside these sub-circuit. Again, the dependent sources, capacitors, resistors, diodes. Everything is there inside the OPA 1641, which has been modeled by the experts from the manufacturer company. And they have given these. So these are the current values from those components. Next, here again the current values. Well, let me scroll it down. Again, all the current values from the sub-circuit. Here, the power dissipation is about picowatt 995, so picowatt or close to 1 nanowatt. Okay, and power from the sub-circuit, power drawn by the sub-circuit is about 54 milliwatts. So it's very quite a useful information about when you are doing electronics hardware design and you want to optimize the performance for the power consumption. You can always refer to this information about designing your software. So it's very good. We are seeing here information is given. So I scroll it down more, and here you see that there is now these voltages. Whenever you see X, U2, U2 is our sub-circuit name, and that is X means sub-circuit. So all these are the voltages across the components inside the sub-circuit. So you can see that. And then let me scroll it down further. Let me scroll it down further. So we have come to know that our operation amplifier alone, the IC OPA 1641, is consuming 54 milliwatt of power. So here your voltage is 0 volt DC, and your power of from the voltage source is V4. That is the input signal source, 0 watt, obviously. And the voltage at the output is 10 millivolts. So tell me now what we can understand from here. Basically, input is 0 volt and output is 10 millivolt. So why is that? So let me show you the schematic screen here. And before that, you also see that all these currents and voltages, in fact, the currents, in fact, and the voltages here, voltages in the brown, currents in the red, have been annotated back on the schematic. So that's done when you finish the operating point analysis. Whenever you will do the analysis, you will have all this wealth of information. Now we can read and understand more and more from this schematic. Okay, so in a moment we'll do that. So right now we see that this voltage source is 15 volt. It is supplying the current of about 1.8 milliampere. Okay, so that's it. Just a second. Right, and what you see here, it is minus sign. It means the current is being drawn by the circuit from this voltage source. Here also minus sign, obviously 15 volt and minus 1.8 milliamp. So total current, total voltage will be 30 volt. Total current will be 1 - 1.8 milliamp multiplied by 2. So the product of current and voltage is our power consumption of the circuit. Either we will say that much power is being delivered by this voltage sources, the power sources in fact now to the circuit, or we'll say the circuit is drawing that much of the power from these supplies. Here you see that this DC value of this voltage source is set to 0 volt. However, there is a peak value of amplitude. If it is a time varying signal, then it has amplitude and frequency. AC, if it is AC signal source, then we'll have to specify the AC volt magnitude, and AC signal magnitude, it can be voltage or current. So obviously you see now, so the current supplied by it is close to 1 micron, so it's quite less as compared to 1.8 milliamp, so it's like 1,000 times lesser than this supply current. And that current is here, obviously 0 volt comes here. This is the DC potential, so here is 0 volt. Here is obviously 0 volt because you have biased the positive pin to the 0 volt. So obviously the output should ideally be 0 volt. However, we see 11 millivolt. Why? Can you tell me that? So answer is simple. Even though there is no externally applied or intentionally applied the voltage difference between the two pins of the op-amp, since the op-amp is a practical, it is a ICOPA 1641, and in the data sheet you will understand there is an offset voltage that is available with this IC, and that gets reflected at the output. Okay, even though there is an external difference between the two inputs is 0, which is right now the case. So this is basically an output offset voltage, or we'll say simply an offset voltage. So then you have this 998 microvolts, so close to 1 millivolt, and the current is also close to 1 microampere. Here also the current through the resistor is like 1 microampere. So this is all the DC operating point situation for the schematic. So as I said before, when you do the low power design and you want to optimize power in your electronics hardware, such information is useful in understanding the performance of the circuit and therefore design a power efficient circuits and the system. So let me take you the remaining portions of these information. So we are here now. Input voltage source is 0 volt DC. Obviously, the power of this voltage source is V4, which is our input signal source, obviously 0 watt, because the voltage, DC voltage is 0. The VO, output voltage, is 10 or 11 millivolt closely, as we see on the schematic. The power consumption of the resistor is about 10 nanowatt. The power consumption of the resistor R2 we have seen up earlier, and the power consumption of the voltage V5, which is plus 15 volt positive voltage supply, is minus 27 millivolt. Minus sign says it is delivering the power. And power, similarly, power consumption, power delivered by this voltage source V1, again 15-volt voltage source multiplied by the current supplied by it is going to give us the value of -27. So total power consumption by the circuit is -27 milliwatt here and -27 milliwatt here. So total about 54 something. So that's what we also saw. So here you see that voltage supply VCC is 15 volt, and that's what we saw. So the total power delivered by these voltage sources is like 27 multiplied by 2, about close to 54, and that is exactly the power consumed by the op-amp and a couple of resistors. That's what we saw earlier. So you see here, probably we are able to find that somewhere here. Can we see that? Where is the power? Right here. Let me scroll it up a bit. Yeah, so here is the power consumption by the R2, again close to 1 microwatt or 995, 1 nanowatt in fact. And here, look at the sub-circuit, that is op-amp power consumption is plus 54. When there is a no negative sign, it means it is consuming the power. Negative sign means it is delivering the power. So hope you found this information quite useful. We have successfully performed the DC operating point analysis, and then we ran also the FFT, but before FFT, we need to carry out the transient analysis, and after transient analysis, we carried out FFT, where we saw the signal spectrum. And one more important analysis we did is the noise analysis. So hope you found this model useful. If you did so, share it with others, with a lot of students, researchers, graduate students in all the universities, institutes, colleges across the world. Hopefully will find this useful to use the SPICE and its potential to run and perform variety of analysis, and most importantly, understand through analysis the performance of the circuit. So stay tuned for more engaging and informative contents in the electronics engineering, technology, and science. And till then, wish you happy learning.